Hi, my name is Sarthak, and in this video, I'll be talking a little more about regression, more specifically, simple linear regression. Let's start off by understanding what it is, and then I'll talk about the key terms that I use in the what it is slide, and then we'll slowly go towards how to use it in a data. In terms of just understanding what simple linear regression is, it is assessing the statistical effect of an independent variable on a dependent variable. Talk more about the term soon. The idea of simple linear regression does not imply causality. In other words, we cannot say that one independent variable or a dependent variable is affected by the latter or the other. We need a little more qualitative assessment of the variables for that. But nonetheless, we can say that it statistically causes an effect or changes something based on another change in another variable. The notation is usually given as y is equal to beta naught plus beta 1 x1 plus ui. Here, y is your dependent variable, x is your independent variable, u is the error term. Beta naught and beta 1 respectively are the slope intercept, and then the beta 1 is your slope. This function is very much akin to the concepts that we've learned in high school, where we use the function y is equal to mx plus c, and if you have to draw parallels, c is equal to beta naught, m is equal to beta 1, and it's the exact same thing. We use a few properties and conditions to apply this, and I'll talk more about this soon. But let's get into the key definitions and terms used that are commonly thrown around when discussing SLRs. Firstly, independent variable. Independent variable is something that is unaffected by any other variables in our equation. When we get into multiple linear regression, there might be an overlap to a certain degree, but cannot be completely affected by the other variable. So, in simple linear regression, perhaps, it is absolutely unaffected by the dependent variable. Dependent variable is the variable that is statistically affected by the independent variable. Now, there can be more variables affecting it, and that is what is absorbed in the error term. We'll talk about the error term soon. The coefficient, the slope of a simple linear regression, the m that I talked about, is called the coefficient. In other words, it's also the rate of change. So when we try to interpret our simple linear regression model, we say that a change in an independent variable causes an x, or the value delta change in our dependent variable. Intercept. Now, this is also commonly written as underscore cons, and this is commonly in stata. It is the intercept of it is the slope intercept of the simple linear regression on the y-axis. R squared, written as r to the power 2, but it is not really a squared value. It is calculated in a different way, but nonetheless, r squared defines the goodness of it. How well does your model fit with the data that is available? P value is essentially a representation of how good your model is in terms of interpretation and predictability on a statistical level. Lastly, you've got the error term. The error term is an end all be all term which absorbs all the variables that are not the effect of all the variables that are not there in our simple linear regression. And you'll learn more about this in our next few slides, where I use an actual data set to work through this. In this slide, let's talk about the core property of simple linear regression, which is conditional mean independence. The simple idea is that your independent variable does not impact the dependent variable. But then why do we have it? When we work through each individual case, each individual level of data, there is some level of error absorbed. As you can see in the image over here, there's a line being stretched out, and then there's a squiggly graph. And that really tells you how the data in reality is, and that line that passes through is your line of best fit, i.e., when you try to predict something, there might be an element of error, but more or less on average, you would get the same value. And this is really projected out through this property. When we talk about conditional mean independence, we mean that the expected value of x given ui, the expected value of the independent variable given the error term is 0, and the expected value of the dependent variable given the independent variable is given by beta naught, which is our slope intercept, plus beta 1, which is our slope coefficient, and x, which is our independent variable. Now let's talk about an actual data example. Here we look at a sample data of height and weight. We're moving in with the assumption that height defines weight, at least statistically. Now we know that that is true on a lot of levels, but let's think about the situation from an absolutely naive perspective. We do not know anything about it. Let's create this. So let's say we've got this data set. We've got about 1,000 observations. We have our weight defined as our y, which is our dependent variable, and height as our independent variable. Now remember that if we switch the roles around, we can still run a regression. But would it make sense? Can you really say that if someone is weighs 180 pounds, then that means that someone would be 5'10" or 5'9" or something of that sort? That's not possible. However, we can switch the terms and assume an element of causality. Again, we have qualitative data on this, but more or less, this is the idea of independent and dependent variables. Now, when we work through our data, we've got 1,000 observations. This data is defined specifically, and we understand what the regressional effect is. I've used two terms, kilos and pounds. The data set is available in our link in both STATA format and Excel. Here's where we talk about the data file that I was talking about. Now, I've already imported the Excel sheet using the code that is mentioned here, but let's create the data. Let's learn more about data as we go through it. Let's define the nature of randomness in our data set. Let's set observations to 1,000. We define x as a uniform value spread out between 130 and 190. We define y as 30 plus zero point 0.8 plus a normal value ranging between 0 and 2. Then let's define y in kilograms, which is the conversion of y, our, our dependent variable, into a kilogram version. And then let's work through the data set. Firstly, let's run the code over here to understand exactly what's going on. Okay, so now we have some amount of data. Let's summarize the data that we've created right now. We note over here that all the data points have about 1,000 observations. When we look at x, which is your height, the mean is 159 with a standard deviation of 16. Similarly, for y, our dependent variable of weight in pounds is 157 pounds. Our weight in kilos is about 71.53. If you do the multiplication, it'll equal out. And then when we create a scatter plot of x and y, you will quickly note that there is a linear regression, that there's a linear path that can be defined between the x and the y variables. This is designed in a certain way, and that's why we see so. However, there can be different versions of this where the data is a lot more scattered. Okay, now let's get back to our data. We quickly rename the variable so that it's easy for us to follow through. Then we perform a regression. Performing a regression on stata is very easy. You just add the term reg, which is a short for regression. You can also use the entire term. Regression, your weight LBS, which is your dependent variable, your height, which is your independent variable. Let's run the regression. Okay, so what do we see over here? We note that our coefficient is zero point 0.8. Our slope intercept is 29.8. Our standard error is 0.0037. Our p-value is 0, and our 95% confidence interval is between this value. What do we mean by each of these elements? The coefficient, as we know, is the slope. So on average, we can say that when a height of a person increases by 1 centimeter, it leads to a zero point 0.8 increase in the weight of that person. I understand that you'll think that, oh, but we mentioned it in our y function that we define it as such. And yes, that is the case, but the regression really helps you understand and identify how that function really plays around, especially with the level of variance added at the end of the y variable. Then we could also do this for our kilos version, where we change the variable that we have on a dependent variable and turn it into kilograms, and we quickly run it. Here you'd see that our coefficient has dropped to 0.36. So when we try to interpret this, we will interpret it as for every 1 centimeter increase in the height of a person, it has a statistical effect of a 0.3 kilo increase in the weight of that person. If you try to multiply that with the conversion factor that we've used above, you'll get the same value as it is in pounds. So the concept does not change, only the unit of measurement does. And hence, this is how you perform regression in Stata. Let's move over to our Excel version now. Now, what I've done over here, I've used the same data that we had in Stata and exported it out to Excel. I've attached the link in the description for the same data set. You can make a copy of it and practice it on your own. Excel natively does not have the ability to perform regressions, and hence what we do is that we use an add-in that's present in Excel to perform this task. Let's go ahead and understand how to add that and how to perform the regression. Firstly, I find this extremely easy, but you essentially type add-ins in your search toolbar and it'll quickly pop up. As you go through this, there'll be another pop-up which talks about the options that are available. Let's select the analysis tool pack, which usually is for statistical and engineering analysis. We enable that, it'll take a couple of moments, and then you'll have that option available. To access that specific option, you go towards the Data tab. The Data tab will have a new section over here called Data Analysis. You select Data Analysis, and another window pops open. It takes about a couple of seconds, but that'll have a list of options that you can work on using statistical tools that are present in this add-on. Now, there are several options, and you can use all of these for advanced econometrics. But nonetheless, we're using right now is regression. Let's activate regression and then it'll show another pop-up. In this, we define our y variable and x variable and work through this. So we know that for the y variable, we're working with our dependent, which is high weight in pounds. Then we define our independent variable x, which is height in centimeters. And then we allow for labels since we're going from the first row to the 1001th row, since you have 1,000 variables in play. We define confidence interval as 95%. We allow the output to come up into a new sheet. We ask for residuals, which is essentially the sum of all the errors, and we ask for a fit plot as well. Let's make this happen. In a second or two, there'll be a new output. And over here, you'll see the same observations as we did in our state output. Let's look at our coefficient. Our coefficient over here is 0.801, exactly the same as we had at Stata. So at the end of the day, the interpretability does not change. But what changes is the process and how we do it. Over here, you'll also note that we have similar levels of t-stat, p-value, etc., etc. The output is going to remain the same. But one thing that I'd like you to pay attention on is the residual output that we have over here. Let's take a quick sum of these values. We know that this is about negative 0.1, negative 1.4 exponent to the power 0. If you look at the value up over here, it's negative 0.0000000 something 147224. Now you'd say that, hey, it's not zero. In statistics, that's the challenge. In statistics, you would not, or you're not always going to find one thing to happen exactly in the way you'd want them to be. Since there is an element of variability, randomness attached to our data, there will be a value. But we look for the closeness towards zero. It cannot be zero point 0.5, but it needs to be somewhere around this range, approximately, to suggest that a conditional mean theorem or property is being satisfied. In other words, it says that on average, when you take the average value of all or the sum of all residual values, you get to a value which is infinitely close to zero or tends towards zero across all observations. This is what is essentially regression. You can perform it on Stata and Excel, but I'd strongly recommend you to learn how to use Stata, Python, or any statistical tool, since observations are not always limited to 1,000 elements. Thank you.